Okay, so here I am. I'm Edoardo Pristeri, a researcher from Links Foundation, Italy, and I'm here today to talk to you about the first part of the knowledge platform, the closest to the shop floor, so the data collection through the Edge Fog Cloud Continuum. So a bit of introduction, some context regarding to the work we did in the knowledge project. The main motivation behind our work is that in the realm of the industrial Internet of Things, modern application should be able to strategically harness the distributed infrastructure, the modern distributed infrastructure that nowadays is available. And so seamlessly integrate edge, fog, and cloud nodes that also Victor has introduced before. These nodes, of course, have difference in terms of computing capabilities and network capabilities. So we have edge nodes that, for example, are more suitable for applications that require low latency and high reliability. Fog nodes, on the other hand, are a bit in between the edge nodes and the cloud nodes. These can be such as small servers on company networks. These are very suitable for applications that tolerate moderate latency, require scalability, and of course, security, because if you use fog nodes, your data is not leaving the company. Cloud nodes, we all know these very well. These are centralized nodes that are in remote data centers. Cloud nodes are very powerful, can analyze large amounts of data, and are very suitable for big data analytics, deep learning, decision support systems, visualizations, at the cost, of course, of increased latency and, of course, a big cost in terms of money, because those servers cost a lot to operate. So this is the target architecture in terms of the data flow that modern applications should aim at. Having the IoT, industrial IoT sensors actuators, close and tightly linked with the edge environment applications. And then we have a fog environment very close to the edge environment, but with more power, and then a separate cloud environment where we can harness all the power of the big data application and the AI algorithms. Of course, reality is often different. We may miss the link with edge nodes because we have interoperability issue. We may be missing a fog environment altogether because the company does not have the computing resource in-house and it's all demanded to the cloud environment. Connection between edge and fog or fog and cloud can have difficulties because of interoperability issues. The data quality is low, and so we can't really harness the power of the data we are collecting. So we have decided to focus on these main three challenges during the course of the knowledge project. Fighting these computing resource dependencies, or at least using it at our advantage. So deploying applications where they are more effective. Then the data diversity and lack of integration. Of course, we have a lot of data types, data collection methods. These pose challenges integrating information in the life cycle of the process. We may think that inside a single production line, there are machines from different vendors that contribute to developing the same product, and we can't use them together because data is not interoperable. And then, of course, there is the information isolation, because security, it's paramount, but it poses challenges because it isolates information between the different stages of the data collection pipeline. So to sum up, we can resume our efforts in these three pillars. The first is data integration, so everything related to collection, integration, and creation of interoperable data models. Data quality, because AI models are like boxes that if you provide them garbage, then you will receive garbage. And so it's very important to refine and ensure data quality for the data that is being collected, otherwise it's useless. And finally, data governance. So all the mechanisms behind the retrieval, the access, and the governance of real-time and historical data, because you have to mix those to create effective AI solutions across the computing continuum. So this is the knowledge approach to these problems. Most of this work has been carried out in what Victor has already presented before, the data integration and management layer. And we have developed 4 main components to address this: the data collection platform, the data quality assurance component, the real-time brokering service, and the historical data storage service components. The data collection platform is a component which goal is to read the pilot devices sensors and database and to expose those to using the unified knowledge data model to the knowledge components. The main innovations of these components have been the southbound interfaces. So we have developed interfaces specifically designed to connect with the custom external protocols already available in the shop floor. So the pilot didn't have to change anything. We just provided a solution to connect with those. The data transformation unifications, as I said, we are using a single data model for simplifying the development of the high-level applications, so they don't have to know about the vendors of the machines, for example. And the MQTT northbound interface exposing the collected data to the whole knowledge platform to the real-time broker. Then there is the quality assurance component, which is a microservice-based component, so it can be customized according to the data quality operations and the kind of data available on a particular use case. These components as a connector service which reads and writes to the real-time broker, so it's able to fetch data from the knowledge platform and can validate data applying data quality rules, for example, relative to the presence or absence of a particular kind of data, checking that values are in the right threshold. And also anonymization service, because if you use cloud devices, it's important that you are safe, that your data is anonymized, and even if a data breach happens, no sensitive information is leaked. So this was very important to us. Then there is the real-time broker, which is at the core of the data distribution of the knowledge platform. These components offer reliable queues and multi-protocol support. We have also enabled the MQTT plugin as well as the MQP plugin, so 2 very popular protocols for enabling knowledge application to connect to these data sources. And we have enabled the Sheldon plugin to enable all the distributed brokers across the computing continuum to have the same kind of data at the same time. This is very important. So application running anywhere in the computing continuum can subscribe and push new data. Last but not least, there is the historical data storage. We already introduced it. This is the component which main purpose is to store data, of course. It can store raw, validated, and anonymized datasets. It can store also datasets for AI models. So all the metadata composing an AI model, this is stored in the historical data storage. And of course, the intermediate simulation results as for the human-in-the-loop approach. So this can be continuously reviewed by the end user, and the user can effectively harness the power of AI through this mechanism. Finally, data replication, all the data, it's available across the computing continuum when needed, on the edge, on the fog, on the cloud. So this approach has enabled us to fix most of the issues that I presented to you earlier in the computing continuum distribution of the data. And so, as you can see, the historical data storage, the data quality assurance, the data collection platform, this component across the 3 main environments that we focus our research on managed us to create a platform that can harness the computing devices across the computing continuum, enabling the deployment of AI models and services where those are most needed according to each use case. I also want to present you some results today. So for data integration, as I said, we have enabled data collection from the shop floor Python environment, implemented this support adaptation layer for interoperability. We have managed to find the data models that managed to include all the required properties and features of all the communication endpoints involved in the knowledge project. We have transformed this data from heterogeneous data sources, provide a proper input to the AI models by aggregating and transforming the data. These are some figures. We have 3 aggregated data sets. We have developed 2 protocols connectors. Those were we have managed to satisfy all the requests of the pilot sources. And we have linked a number of 26 data sources to the knowlEdge platform during the project. These are very good numbers. We have solved challenges in the data quality realm as well. We have developed this modular edge pipeline to acquire and process the shop floor data, so it can be customized case by case according to the end user needs. We have provided modules and algorithms aimed to ensure data quality, and we have made sure that privacy and confidentiality of collected data by masking the sensitive data at the edge. So sensitive data does not leave the edge environment, it stays where it's born, and both for real-time and historical data sets. So end users are more confident in using AI applications. These are the figures. So we have developed 6 possible anonymization rules, algorithms suitable for different kinds of data sets. We have anonymized 2 data sets. We have validated 26 data sets using the 10 possible validation rules. So we support all the major data formats and data types, and we have rules for validating those. And for creating all of these, we have used the 4 developed data quality modules. Relative to data governance, we have managed to store historical data at the factory premises for data mining purposes and visualization purposes. This is important for optimizing the flow of data and not have to resort on cloud resources, which are very expensive. We have developed these effective queuing mechanisms that I described to you before for live data, providing this failure-free data propagation across the nodes at the edge, fog and cloud, so the whole computing continuum. This is very important when deploying AI models, so that those can be deployed where they can be, where their execution can be most effective and more efficient, and so they are able to have the same kind of data across the computing continuum. You don't need to know where to deploy the AI models. The orchestration process can do it, all of this automatically. We have ensured low footprint on the processing and storage requirement and latency of the developed artifacts. So all of this data, it's very efficient in terms of storage and in terms of latency, so it can be accessed very quickly. And we, of course, all of these data orchestration and data access methods have been considering privacy and confidentiality needs of the fog computing paradigm, because we have done all of these, of course, following the industry standards security practices. These are the figures relative to data governance. We have these 3 environments synchronized, edge, fog, and cloud. The historical data storage component has stored more than 50 time series data, each referring to one kind of device. And its APIs support 11 languages. So this is very developer friendly. So if a third party wants to develop an application to integrate with knowlEdge platform, this is very easy because we support a lot of programming language which are with our data access paradigms. We have also learned some lessons, and there are some open challenges. The first is that the REST protocols, which is de facto standard in most industrial services, has limitations because it struggles with large data quantities. We have circumvented this problem by implementing data splitting and retrievals in smaller segments, although we have found that this requires frequent queries and such increases the computational footprint on the edge service. So this is an open issue. And although we have discovered that MQTT is very powerful because it eliminates all the needs for synchronizations and enhance the data handling efficiently, this is usually limited to sensor industrial context. REST is much more present, but it's gaining traction. And another lesson learned is about the data quality validation rules, which are not always clear from the beginning. So an iterative process has to be have in mind if you want to implement this at your premise, because the challenges appear as soon as you start to work with the data. So it's different to know in advance. An iterative process is needed for this. So just final remarks in discussion. These are this is where you will be able to find a lot of more technical details about the work we have done. When there is the knowlEdge project website, the knowlEdge deliverables, and the knowlEdge scientific publication. This is the